As we start to talk about blood flow and blood pressure, it's important to remember that our heart is a dual action pump and that it pumps to all of our organs in parallel, not in series. For those of you that are in physics, this is going to sound like trauma all over again, but it's important to make this distinction. There are several benefits for having our blood flow to our organs in parallel. The first has to do with our concentration gradients. If blood flow was in series, the blood would go to the muscles, then all of that blood would go to the kidneys, then all of that blood would go to the digestive system, and then to the brain, and then to all the rest of our organs. If this were the case, at each point in time, the muscles would pick up oxygen and drop off carbon dioxide. The kidneys would then pick up oxygen and drop off carbon dioxide. The digestive system would then pick up oxygen and drop off carbon dioxide. How would this affect our gradients? By the time the blood made it up to the brain, the blood would already be significantly lower in oxygen and higher in carbon dioxide. When we talked about diffusion in chapter 1, we said that the larger the concentration gradient, the faster diffusion will occur. Oxygen in the blood is almost equal to what is in the tissue of the brain. No diffusion would occur. This would prevent tissues further down the stream from getting an adequate oxygen supply. The reverse would also be true. There would be significantly more carbon dioxide in the blood than in the cells, which would prevent carbon dioxide from entering from the cell tissue going into the bloodstream. The tissue closer to the heart would experience a situation like this, where the cell has low oxygen and high carbon dioxide, and the blood has high oxygen and low carbon dioxide. The rate of diffusion would be quick because the concentration gradient is large, and oxygen and carbon dioxide would move as follows. The oxygen in the blood would move into the cell tissue, and the high carbon dioxide in the cell would move towards the low carbon dioxide in the blood. Again, if circulation was in series, when we reach the middle tissue, we would see a situation like this. The cell would still be low in oxygen and high in carbon dioxide, but the blood would only have moderate oxygen and already have moderate carbon dioxide because of the exchange that happened closer to the heart. This would change diffusion by decreasing the rate and the amount because the gradients are closer together. Therefore, only a small amount of oxygen would diffuse into the cell, and only a small amount of carbon dioxide would be able to exchange into the blood. When we reach far downstream, the tissue furthest from the heart, the cell's condition would still be the same. They would be low in oxygen and high in carbon dioxide. However, by this time, the blood would have already passed through many organs and diffused most of its oxygen into tissue further upstream. Already received carbon dioxide from all the previous cells. This would almost limit or prevent exchange from occurring between the blood and the cells. This would result in a change in pH, where the cell would become greatly more acidic and have less and less oxygen in order to make ATP. By having a parallel circulation, this ensures that every tissue receives blood that is the same concentration with a high oxygen concentration and a low carbon dioxide concentration. This ensures adequate gradients to allow for diffusion to occur between the cells and the blood. Another advantage to having a parallel series is that blood flow to certain organs can be increased or decreased depending on metabolic demand. An example of how the body is able to regulate blood flow in a parallel series is during exercise. During exercise, the skeletal muscles demand more oxygen and produce more carbon dioxide, which results in them needing more blood. In a series component, we would not be able to regulate the amount of blood that went to the muscles because it would just be in its order in the chain. However, through a parallel series, we can increase the amount of blood flow that's given to the muscle and decrease that flow to other tissues. As you can see, during exercise, we get a condition like this, where the muscles receive more blood flow, the digestive system receives less. This allows for the muscles to receive more blood flow, while inactive tissues receive less. The opposite can happen after we eat. After we eat, the skeletal muscle is relatively inactive, where we need increased blood flow to our stomach and small intestine in order to break down food and get those nutrients into our bloodstream. In order to compensate for increased digestive blood flow, we see a decrease in blood flow to the muscles and other inactive tissue. The one organ that remains relatively steady in the amount of blood that it receives is the brain. Just like when we talked about glucose, and the brain will always have the glucose that it needs, the brain will always work to maintain a steady rate of blood to the brain. Too much blood flow to the brain could result in an aneurysm or a breaking of those blood vessels. Too little blood to the brain could result in oxygen deficiency. The natural question you should have from our previous slide is, how do we vary blood flow when we're exercising versus when we are post-exercise? Blood flow depends on the pressure gradient, so this is P at the start of the vessel versus P at the end of the vessel, and vascular resistance. Vascular resistance is the friction between the blood and the blood vessel. This is one reason it's so important that there is a difference in pressure between our left ventricle and our right atrium. The left ventricle is responsible for pumping blood into the systemic system. If blood pressure in the atria was 100 millimeters of mercury and the pressure in the left ventricle was 100 millimeters of mercury, there would be a zero pressure gradient and blood flow would not occur. An example of this would be in case 1. The left ventricle has a pressure of 100 millimeters of mercury and the right atrium has a pressure of 2 millimeters of mercury. The pressure gradient in this case would be 98 millimeters of mercury. In situation 2, the blood pressure in the left ventricle is 80 millimeters of mercury and the blood pressure in the right atria is 2 millimeters of mercury. This would result in a pressure gradient of 78 millimeters of mercury. If the resistance in both situations was the same, for this example 1, we would say that blood flow in case 1 would be greater than blood flow in case 2 because of the larger pressure gradient. Another small but vital detail is remembering that it's not the absolute starting pressure that we're concerned about. We're concerned about the overall change. So as you can see, vessel 1 starts out at 80 millimeters of mercury and ends at 20, which has a total change of 60 millimeters of mercury. Vessel 3, on the other hand, starts at a larger pressure at 120 millimeters of mercury, but drops to 60 millimeters of mercury. It therefore has a change of 60 millimeters of mercury. Therefore, if the resistance is the same in both vessels, vessel 1 and vessel 3 will have the same blood flow because they have the same change in blood pressure. If we look at vessel 2 compared to vessel 4, even though vessel 2 starts out at a lower pressure than vessel 4, it has a drop of 20 millimeters of mercury compared to vessel 4's 10 millimeters of mercury. Therefore, vessel 3 will have a greater blood flow than vessel 4 if resistance is the same because it has a greater pressure change. Vascular resistance is a little bit more difficult to calculate because it is the composition of the viscosity of the blood, the length of the vessel, and the radius of the vessel. If we think about viscosity, you could think about honey flowing out of a container versus ketchup versus water. The honey moves the slowest out of the container because it has the highest viscosity. Ketchup would move second, and water would move the fastest. Water, of course, has the lowest viscosity. Viscosity of the blood stays relatively constant but can depend on hydration status. As we become more hydrated, there is a higher concentration of water within our blood. This creates greater amounts of plasma. Greater hydration leads to less contact between red blood cells and the vessels. This decreases blood viscosity. As we become dehydrated, we lose plasma volume. The red blood cells become more concentrated and have more contact with the blood vessels. This increases viscosity and increases resistance. If we increase resistance, we are going to see a decrease in blood flow. The length of our vessels remains constant. The great example of this is comparing the pulmonary circulatory system versus a systemic circulatory system. The pulmonary circulatory system is much shorter compared to the systemic circulatory system. This means the pulmonary system has lower resistance compared to the systemic system. This is why our left ventricle has to create more pressure in order to overcome the length of the system. If the lengths were the same, the starting pressures could be the same. But since the blood has to travel a further distance in the systemic system, the left ventricle has to shoot that blood out with a greater pressure in order to get it all the way back to the right atrium. In contrast, the pulmonary length is much shorter, so in order for the blood to travel from the right ventricle to the left atrium, it needs to generate less force to push that blood through that shorter distance. As you can see, because the pulmonary system is shorter, it has less resistance and therefore needs less of a pressure gradient for the blood to reach the end of the tube. The systemic system is longer, which increases the resistance that it has, and therefore to have equal blood flow, it needs to create a larger pressure gradient. In our last quiz, we talked about how pulmonary blood flow needs to be equal to systemic blood flow. This prevents blood from backing up in either system. In order for this to be the case, we have to look at the pressure at the beginning compared to the pressure at the end and the resistance in each system. This is an oversimplification, but an easy way to understand why pulmonary pressure is less than systemic pressure. Pulmonary blood flow needs to be equal to systemic blood flow in order to prevent congestive heart failure. If we fill in our variables, we can see pressure at the start of the heart, leaving both ventricle, minus pressure at the end in both atria over resistance dictates blood flow. Now let's assume that the radii and the blood viscosity are equal in both systems. In most cases, the radii will not be equal, but for the simplicity of this, let's say that they are equal. And if they're equal, they're not going to impact the difference between the blood flow of the pulmonary system or the blood flow of the systemic system because they're the same in both systems. We also see that atrial pressure is equal in both systems. Now we can look at the length of the tube. Again, a simplicity, let's say that the pulmonary system is 1/2 the length of the systemic system. We know the pulmonary system is shorter than the systemic system, so let's say it's half the length. If it's half the length, in order for these two to be equal, we have to have a greater difference of pressure in order to overcome the longer length of the systemic system. For the purpose of this example, I've arbitrarily assigned the length as 30. The difference of pressures is equal to 58, and its length is half the length of the systemic system. We know that the systemic system has to have double the starting pressure as the pulmonary system. If we take both systems, starting and ending pressure divided by resistance, we see that both the pulmonary and systemic system both are going to pump out 3.87 liters per time unit. Now, within both systems, the radii can change and the starting pressure within both systems can change. Blood viscosity and length are going to remain relatively stable from one point to the next. One detail worth pointing out, in the resistance equation, we see that radii is a factor of 4. This means that small changes in the radii of vessels results in exponentially great changes in resistance. If there are large changes in resistance, we're going to see large changes in blood flow. Now here's an example of how changes in vessel radii result in large changes in blood flow. Again, let's say that the pressure going into the vessel is the same for all 3 vessels. Let's call it 120 millimeters of mercury. And the end pressure is 0 for all 3 vessels. So the total change is 120 over the resistance. The blood and the length of the vessels are the exact same, so those will not play a factor. The only factor in resistance is going to be the radii. Just by looking at the vessels, you can see that in vessel 1, less blood is going to come in contact with the edge of the vessel wall compared to vessel 2 compared to vessel 3. This contact between the blood and the vessel wall is what causes friction and therefore increases resistance of the blood flow. So once we've calculated the resistance, we see that 1 over 10 to the 4th gives us 1 over 10,000. When we divide a blood flow with a change of pressure of 120 by 1 over 10,000, we see a blood flow rate of 1,200,000. For vessel 2, we take the resistance of 1 over 5 to the 4th, which gives us an amount of 1 over 625. If we take blood flow of 120 millimeters of mercury pressure difference divided by 1 over 625, we get a blood flow rate of 75,000. This is 1/16 of vessel 1, which makes sense because vessel 1 is double the size of vessel 2. So it has 16 times less resistance than vessel 2. If we look at vessel 3, it is 1 over 2 to the 4th, which gives us 1 over 16. With 120 millimeters of mercury pressure difference divided by that 1/16, we get a blood flow of 1,920. This is 1/39th of the blood flow of vessel 2. Therefore, changes in radii result in exponential changes in blood flow.